Welcome. My name is Erik Larsson and I'm with Linköping University, Sweden. So I'll be talking about radio waves technology for sub-6 GHz 6G physical layer as being developed in the Horizon 2020 Reindeer project. So the concept of radio waves is to use a form of MIMO technology with lots of service antennas, and where these service antennas are spread out and integrated naturally into the environment. So it could be, for example, antennas that are integrated into the facade of a building outdoors, or into the walls or the ceiling, or even furniture indoors. So here's an illustration of that, where antennas are everywhere in a room. And in a particular incarnation of this architecture, one can also envision to have panels of antennas that are co-located, and then the panels themselves interconnected. Okay, so radio waves then inherits a lot of the features that made cellular massive MIMO so successful. Specifically in cellular massive MIMO, we had cells, and each cell was served by a base station or an access point that comprised an array of co-located antennas. And the preferred way of operation of cellular massive MIMO is in time division duplex, where we can exploit reciprocity of the uplink downlink in order to for the base stations to learn both the uplink and downlink channel response by measuring uplink pilots sent by the terminals. And this was good because it gave us an array gain, which in turn translates immediately into improved coverage and improved quality of service, especially at the cell borders, and also potentially into a reduced radiated power. I mean, with 100 antennas, we gain a factor 100 in link budget with beamforming, which in principle could translate into a savings of a factor 100 in power. The reciprocity-based beamforming in TDD mode is scalable with respect to the number of service antennas. The pilot resources required are only dependent on the number of terminals that we want to multiplex simultaneously. Another advantage of TDD and reciprocity-based operation is that no prior assumptions on propagation are required. Well, in fact, one can do better if one has some prior knowledge of what the propagation environment and the channels look like, but it's not required for massive MIMO to work. And it's also agnostic to the topology of the antenna arrays themselves, which is an important point. So again, there are no assumptions made on neither on what the antenna arrays actually look like, nor on what the propagation environment is like. The high spatial resolution that an antenna array offers gives us high multiplexing gains, and it can aid in resolving collisions even during the random access phase. So even in, even resolving collisions among preambles or during grant-free random access for that matter. Channel hardening is an important phenomenon that's seen in massive MIMO systems. Essentially, it means that the effective channel that each one of the terminals sees is nearly deterministic, so it fluctuates only very little across frequency and time for that matter, which has the important implication that, scheduling over the frequency domain, for example, becomes almost irrelevant or unimportant. So we better give all the terminals the full bandwidth simultaneously and then multiplex them spatially as well. And this hardening also simplifies not only scheduling, because the need for scheduling essentially goes away, but it also simplifies a lot of other tasks in the system, like power control, for example. So radio waves inherits pretty much all these highly attractive features of cellular massive MIMO. And here is an example of what we see that this technology can offer more quantitatively. So in this example, we have a room of size 40 by 40 by 10 meters. So we're indoors. We have the we have 200 terminals to serve, and these terminals are spread out in the room. That's the figure here, spread out in the room. And we want to offer everyone a 4 bits per second and hertz spectral efficiency simultaneously. So simultaneously means that if we run OFDM, for example, then all these users get 4 bits per second and hertz on all the subcarriers in the system. And we want to do this by using 512 patch antennas. And then the two scenarios that we compare are, on one hand, a radio waves deployment where the antennas are spread out on the walls, like in the figure here, with several wavelengths in between. So there's no real antenna array in the classical sense. It's more like antennas are spread out over the walls. And in this particular configuration, we have them as stripes. So each wall carries like 4 stripes like this. So that's the radio weaves configuration, and the competing technology would be to serve these terminals using a co-located conventional antenna array. So for comparison, we also consider that, and then we had a candelabrum style array with half wavelength separation among the antenna elements, and the array was mounted on the hanging from the ceiling in the room. So that's the candelabrum co-located array. And the figure to the left here illustrates how much power that is required in total by the array on downlink versus the probability of outage. Outage means that we can't offer this 4 bit per second and hertz quality of service to everyone simultaneously. Okay, and the randomness here is only over the locations of the terminals. So there is line of sight in the room, and the users are randomly located. So being here to the left, and the steeper the better in the plot. And then we have first the blue line, which corresponds to the candelabrum style co-located array. And then we have various versions of the radio waves concept. And to the left here is the one that I illustrated in the figure over here, with let's see, quadruple strip 4 walls. This is that all the 4 walls have 4 strips of antennas. And the important observation, of course, is first that with high probability, so with outage well below 10 to the minus 4, the total output power required is on the order of 20 dBm, which is extremely low. And also that in comparison, if we compare the candelabrum array to the radio waves deployment, then there is a difference here in required output power, which is more than 4 orders of magnitude. And this is all because of, 2 things really. First, there's of course with the radio waves deployment, it's more likely that if we put the user somewhere here at random in the room, that he'll be close to a bunch of service antennas. So there is a gain in path loss. But the most important phenomenon here is that in the radio waves deployment, a terminal will, or rather the set of terminals that we serve jointly together, will experience favorable propagation with very high probability. Favorable propagation means that the resulting effective MIMO channel has a substantially full rank, whereas in the case with a co-located array, then as seen from the array, it's very likely that 2 terminals will be very close in angle and not separated well enough that we can actually transmit to separate streams to them without using a lot of output power. So that's really the reason for the enormous increase here in radiated power that would be required by a conventional style co-located massive MIMO array as compared to the radio waves deployment. Okay, use cases that radio waves will support. First of all, augmented and virtual reality services that will require high data rates, low latency, and high reliability. And then location-based information systems and services, like tracking of goods, for example, patient finding in hospitals, tracking of robots and flying vehicles and so forth. And monitoring and interaction in real time, which includes smart home automation, humans and robots co-working, monitoring of patients, maybe with in-body and wearable sensors, and so forth. Another, well, if not use case, at least application, say, of radio waves technology would be to support emerging infrastructure for distributed and federated machine learning. So here the idea is that we have a server, and the server maintains a machine learning model, and then we have devices that make their own observations of, say, well, training data that is going to be used to train this model. And these devices don't want to share their training data directly with the server for privacy reasons. So the way federated learning works is that, well, the server broadcasts its current version of the learning model, and each one of the devices obtains their own training data and then computes an update to the model and feeds this back to the server. And this is an emerging field in, say, machine learning, where wireless communications is likely to play a major role once we have devices that are wirelessly connected and are going to participate in this training process. Potentially the number of devices here could be huge, and we see that radio waves technology will be an enabler for making this happen, especially when we have very large numbers of devices. Okay, technical challenges. Well, one perhaps obvious technical challenge is to implement a system like this, to make it work with the baseband processing and to make that processing scalable. It is currently somewhat of an open question what the best topology is for, say, the digital processing, whether the antennas should be connected in a tree structure or whether they should be connected in some kind of a mesh or like a tile like over here, and if so, whether everyone should be connected in the mesh or only some of the connections should be there. One thing that is known is that it is possible to, say, an uplink to implement the globally optimal detector for the uplink data in a distributed fashion with a frontal load that is independent of the number of antennas without losing optimality, and that's done in these papers here for those of you who are interested in the details. Another technical challenge is, of course, reliability and low latency, and also in the context of massive access, where we have a lot of devices and potentially a lot more devices than what the channel coherence interval allows us, in the sense that so we have more devices than samples in the coherence block, which means that we can't afford to give every device a unique orthogonal pilot sequence, and this inevitably causes then collisions in the random access phase. Making that work in the radio waves context is a major challenge. Some of the general challenges on MAC layer with ultra reliability and low latency and massive number of devices are described in the paper here that I hope will be of some interest. And a third technical challenge that I'd like to mention also is to communicate with energy neutral or passive devices. So passive device could range from a device that only does backscattering of the incoming RF to a device that might have a small capacitor or a tiny battery that can be charged through some form of energy harvesting. And one thing that's known here from previous literature is that, well, with a full duplex MIMO reader, it's possible to communicate with backscattering devices and obtain an array gain which is the same order or equal to what we have for coherent communication with MIMO. And the question, of course, is how to make this work in practice in the radio waves deployment. So that's what we are working on in the project. Very good. Okay, with that I'll conclude here. Thank you very much for listening. And if you have any questions, I'll be happy to take them either in the Q&A or just offline through email. Thank you very much.